Hello guys, my name is Mohammed Izhaan Khan. Currently, I'm pursuing my degree in Civil and Environmental Engineering from IIT Patna. We were solving the exemplar questions of chapter number 12 of Physics, Atoms. So, in the last class, sorry for the delay. In the last class, I think we had done till question number. Let me check. Okay, so in atoms. Okay. So we have done the VSA. We have to start from the short answer type of questions. So question number 19. All right. So yeah, correct. So let us start from question number 19 now. There's a positronium. They have told us about a positronium first. Positronium is just like a H atom with a proton replaced by the positively charged antiparticle of the electron. All right, called the positron, which is as massive as the electron. Correct. What would be the ground state energy of positronium? So this is the concept. Now I'll tell you about the key concept behind this question. All right. So in these type of conceptual questions, or everything that you need is concept. Okay. You don't need to practice hundreds of questions. You just need to get the correct concept behind these questions. So positronium can be written as PS. Okay, it is a system consisting of an electron and its antiparticle, which is called a positron. So electron ka antiparticle is called a positron. All right. Okay. So a positronium is a system consisting of positronium consists of an electron plus a positronium. Okay. So this is bound together in an exoatic form. Okay. So this is an unstable form. All right. This whole system is unstable. First of all, this you need to know. All right. Okay, so let's start this question. So, as in the new hydrogen atom that is called the positronium atom PS, proton is replaced by a positron. Yeah. So, a proton has a mass m, and a positron has a mass me by 2. Okay, so the mass of positron m is mp minus plus me minus, and this mass m can be written as mp plus me initially, which is 2me. All right. Now I like the positronium mass. Positronium mass can be written as simply me by 2. So as En is minus 13.6, and so energy of positron will be what? I'm sorry for the disturbance. So yeah. So we already know the formula for En. En whole formula is n plus E4 8 epsilon naught n square h square. Okay. So if you have to only see about the n and e, so it can be written as minus 13.6. You already know this. Okay. So energy En will be 13.6 divided by 2, since this is 2. Since the mass of positron will get into half, so En will be minus 6.8 electron volts. You only have to check for the mass. You only have to change the mass. So now question number 20. Assume that there is no repulsive force between the electrons in an atom, but the force between all. So assume that there is no repulsive force between the electrons in an atom, but the force between the positive and negative charges is given by the Coulomb's law as usual. Under such circumstances, calculate the ground state energy of a helium atom. All right. So total energy of an electron in the nth stationary state of hydrogen atom or hydrogen-like atom with atomic number Z is called the कैसे लिखते हैं? Energy E can be defined as minus because it is an attractive energy ME4 8 epsilon naught का whole square h square dot z square upon n square. So इतना चीज constant रहता है and the value for z and n can be changed for the excited state and rest. तो energy को हम लोग simply लिख सकते हैं. Something that we have to remember. इसको भी याद रखना है. We have to remember this and simply अगर simple questions आ रहे हैं then this is more than enough for you. इतना electron volt. So Z can be changed or N can be changed. N is the excited state. The ground state is for N equal to 1 is the ground state. And for helium nucleus, Z is equals to 2 and N is equals to 1 for ground state. So energy will be what? E will be minus 13.6. Z की value 2, 2 का square 4 and divided by 1 electron volt. So solving this 4, 6, 4, 2, 4, 4, 54. So 54.4 negative electron volt. So this is your energy. We have to remember this. Energy is equals to minus 13.6 Z square upon N square electron volts. Alright. Moving on to the next question. Using Bohr model, calculate the electric current created by the electron when the H atom is in the ground state. Alright. So electric current क्या होता है? I is equals to Q by T. Okay. The charge divided by the time. So if we want to write it, we can write it as Q times frequency. Alright, where F is the frequency. Now, writing about F which is the frequency can be written as number of revolutions per unit time. So I can write it like this, where A naught is the radius and V is the velocity. Alright, so the electric current is given by, now I've already written as QF. So now the next thing that we can do, we can simply write the current as Q times frequency, so 2 pi A naught upon V and charge Q, any charge for an electron is E. Alright, so the electric current has been given by this. Now, moving on to question number 27. Now, question number 22nd. How many questions are there? Let me see. Okay, so we are just at the word of finishing it. Now, question number 22nd. Show that the first two frequencies of light that is emitted when an electron falls to nth level from levels higher than n are approximate harmonics in the ratio 1 harmonic. The ratio 1 is to 2 is to 3. Okay, when n is greater than 1. All right. So writing about the frequency, we all know frequency can be written as a constant times z square. Okay. Check for this value for this constant n plus n dash का square minus 1 upon n का square. तो अब यहाँ पे हम लोग को दिया हुआ है that it has been given that n is greater than n dash. N dash is 1, 2, 3. Okay. Now, so neglecting the higher terms as n is greater than n dash, then अच्छा मैं करके दिखा देता हूँ. So we can write frequency as, now I'm writing constant, Rydberg constant r z square. अगर मैं n को common ले लूँ, n square को I mean, so I take n square common. Inside will be 1 plus n upon n dash upon n, है ना? N dash upon n इसका whole square minus 1 upon n का square. Alright. So now if we try to solve this, तो c r z square 1 upon n square तो common ले चुके हैं already. So हाँ इसको ऐसे ही रखते हैं अभी. And we all know that we can write it 1 plus n dash upon n raised to the power of minus 2. And since n is greater than n dash, so it is a very small value. So when this is a very small value, less than or less than, I mean, if this value like 1 plus a raised to the power of something like 2 can be written as 1 minus 2a when this a is less than 1. Alright, we already know this. So this is the same thing that we are going to write over here. So I can write it as 1 minus 2 n dash upon n. and minus 1 upon n square. Alright. Now moving forward, I can open this up. CRZ square 1 upon n square minus 2n dash upon n cube minus 1 upon n square. Alright. So what will be left with? CRZ square 2n dash upon n cube, right? 2n dash upon n cube. Now, if you see CRZ square 2CRZ square upon n cube, this is acting as a constant and we are only left n dash. And now the value for this n dash is in the ratio 1:2:3. So the frequency will also be in the ratio of 1:2:3 and so on. In the same harmonic fashion, it will move on. So now moving on to question number 23rd. Alright, so in question number 23rd, what is the minimum energy that must be given to a H atom in ground states so that it can emit an H gamma line in Balmer series? If the angular momentum of the system is conserved, what will be the angular momentum of H gamma photon? Okay, so as we already know that this H gamma is basically what? It is a spectral line in the Balmer series. Okay, and I apologize for disconnecting every now and then. There's basically a survey going on in my hostel right now. Yeah. So continuing from question number 23, what is the minimum energy that must be given to a H atom? Alright, we read about this question now. If we talk about the Balmer series, and for the Balmer, when is it formed? It is formed when an electron falls from n equal to 5 to n equal to 1. So if the electron is in the ground state, for it to go to n equal to 5, we must give it some energy. So writing about that, energy E can be written as E5 minus E1. Okay, so E5 I am writing right now. It will be what? If I write 13.6 upon 5 per square minus 13.6. Alright, this is also in minus. So minus 13.6 divided by 25. It will be 0.54. So minus 0.54 plus 13.6 will be 13.06 electron volts. Since angular momentum is conserved, so the angular momentum of H double gamma line, now we can write it as angular momentum is conserved, right? So L5 minus L2, 5H minus 2H, it is equal to 3H, will be equal to 3 times 6.63 into 10 raised to the power of 10 minus 34. And now this can be written as 19.89 into 10 raised to the power of minus 34. And the unit for H is what? Kg meter square per second. Okay. Now, we have question number 24 for long answer types. So the first four spectral lines in the line series of an H atom are given. Okay. So if instead of hydrogen we consider deuterium, calculate the shift in the wavelength of these lines. Alright. So this is the question that we have. So the first four spectral lines, if I write, number one will be 1218 angstrom, lambda 2 1028 angstrom, lambda 3 974.3 angstrom, and lambda 4 will be 951.4 angstrom. Alright, if instead of hydrogen we consider deuterium, calculate the shift in the wavelength of these lines. Okay, so now what we know, 1 upon lambda is equals to R input constant, 1 upon n final ka square minus 1 upon n initial ka square. This is the state in which the electron is currently. So lambda is inversely proportional to 1 by R, or we can write lambda deuterium upon lambda hydrogen can be written as RH upon R. This is the Rydberg constant for hydrogen atom, and this is for deuterium. So if the state is same, then we have to just check for the different like deuterium. We know already for the hydrogen. Now Rydberg for hydrogen can be written as Ne electron is to the power of 4 8 epsilon naught CH cube. Alright. Now, and for the deuterium, I can write as this M electron. I can also introduce the reduced mass mu h over here. This will help you because this is the point where the change will come between the two atoms. So R for deuterium will be reduced mass of deuterium times E4 8 epsilon naught CH cube. Alright. So now I know RH upon RD will be what? It will be mu reduced mass of hydrogen, reduced mass of deuterium. Simple. Now we already made the relation between the RH and RD. Just equating that. If I equate that thing, lambda D divided by lambda hydrogen will be mu times H and mu D. This is for reduced mass for hydrogen, reduced mass for deuterium. So now how to write reduced mass for hydrogen? Mu H will be mass of electron upon 1 plus mass of electron divided by M. So simply writing it like this. M upon 2M. Alright. Okay. And mu deuterium will be the same. Right. No, in mu deuterium 2M will come, right? Mu deuterium will be 2M dot Me. If I take the M out of it, and 2M down here also 1 plus Me upon 2M because 2. So basically this is the only part for mu deuterium. I have multiplied and divided 2M for it to be easy for me to visualize that it can be written like minus Me upon 2M. Alright. Now, where M is the mass of proton. What is M? M is the mass of proton. Mass of proton. Alright. And for hydrogen, mass is equals to M. For deuterium, mass is equals to 2 times M. Simple. Alright. Now, if I want to write mu hydrogen divided by mu deuterium will be what? 1 minus mass of electron divided by 2 times M. And just calculating it, mu h upon mu d will give me this. 40. So now calculating this is going to get me so this is going to become 0.9997. Basically, I've used this relation that mass of proton can be written as 1840 times mass of electron. Okay, so this is the ratio between the reduced mass. So this can be the ratio between the lambdas too. So lambda D upon lambda H can be written as 0.99973. Alright. So now what do we have? तो लैम्डा एच की हम लोग के पास वैल्यूज थी 1218 एंगस्ट्रॉम 1028 एंगस्ट्रॉम 974.3 angstrom and last value was 951.4 angstrom. If we put lambda h over here, we can calculate lambda d easily. So lambda d for 1218 will be what? 1218 into 0, it will be something around 1270. You need to calculate this, okay? I'm just, because it is 0.999, it is approximately equal to 1. So I'm writing it like this, but you need to calculate this, okay? For it will be 973 something. It will be 950 something. Alright. So calculate it. Put the value of lambda h over here, and you'll get lambda d for each of these values. Okay, so the next question is really a long question. So deuterium was discovered in 1932 by Harold Urey by measuring the small change in the wavelength for a particle transition in hydrogen and deuterium. This is because the wavelength of transition depends to a certain extent on the nuclear mass. Alright. So the nuclear motion is taken into account, and the electrons in nucleus revolve around their common center of mass. Such a system is equivalent to a single particle with a reduced mass mu, revolving around the nucleus at a distance equal to the electron nucleus separation. So here mu is equals to MEM divided by ME plus M. All where M is the nuclear mass, ME is the electronic mass. Estimate the percentage difference in wavelength for the first line with the Lyman in proton and deuterium. Mass is given and the rest of the things are also given. Okay, so writing about the total energy first. No need to write in the short form, because whenever there is a long question, write the whole formula, because see, I told you that energy can be written as minus 13.6 z square upon it. Alright, but what happens is sometimes in the long question types, they give you some hint that something in this is also changing. The constant was over, which was over there, but something inside this will be changing. So first write the whole equation, then see if it is changing or not. If it is not changing, just write it as 13.6. You already know the value for this. So what is the formula for E? So write in the reduced mass state. So in the nth orbit, I'm writing z square E4 divided by 8 epsilon naught whole square h square n square. Alright. So mu is the reduced mass of electron. I'm writing it over here. Mu को simply लिख देता हूँ mass defect, because it is the reduced mass of electron, proton, neutron, all three. So it is the mass defect over here. Now, if I write for the hydrogen, EH can be written as mu reduced mass of hydrogen, Z के लिए होगा E4 8 epsilon naught whole square h square and 1 upon n1 square minus 1 upon n2 square. तो डिफरेंस ले रहा हूँ ना, तो it will be what 1 upon 1 का square minus 1 upon 2 का square. So I can write it as 3/4. So simply put, ठीक है. So this is the EH. Now E can be written as H nu, which is equals to H lambda. Same goes for what? Lambda hydrogen can be written as H upon energy of hydrogen. Simple. तो lambda hydrogen मेरे लिए easy हो गया. और simply I can write the mu hydrogen. Mu hydrogen के लिए mu H E4 8 epsilon naught का square h का cube 3/4. Alright. H nu is equals to E था ना, तो वहां से. Now if I want to calculate the percentage difference in wavelength in lambda can be calculated as lambda p minus lambda h whole divided by lambda hydrogen into 100. Okay, lambda d. Alright, now if I need to calculate for this, what am I going to do? I've already calculated delta E. Delta E can be written as lambda d lambda hydrogen minus 1. Okay. Percentage में चाहिए तो into 100. Alright. So now H nu can be written as mu times E4 whole divided by 8 epsilon naught का square h का square 1 upon n1 का square minus 1 upon n2 का square 1 upon n1 का square minus 1 upon n2 का square. तो H nu है हमारे पास. तो now I'm writing for mu E4 8 epsilon naught whole square h cube 1 upon 1 square 1 and so mu can be written as C by lambda. Now writing for lambda is mu times E4 8 epsilon naught का square C h cube 1 upon n1 का square minus 1 upon n2 का square. Now this proves that lambda is inversely proportional to h, since the mass defect of epsilon, h are all constants for an atom. So I can write the equation 1, which is the change in the wavelength. Delta lambda is equals to mass defect of hydrogen, mass defect of deuterium, minus 1 times 100. Alright. Now we have to calculate for the mass defect. Okay, so the calculations must be done now. So now I'm just going to be a little fast now, because I think that you wanted to know what is mass defect and rest of the things. So MD divided by mass electron plus MD. Alright. So since mu h is the reduced mass, we already know. Then the frequency of the first time in series can be written as h frequency can be written as mu h e for 8 epsilon naught per square h cube h square. I'm sorry. 1 minus 1 by 4 will be 3 by 4. Okay, this is the part 1. And now, does the wavelength for the transition lambda h can be written as simply mu hydrogen E4 8 epsilon naught per square h cube c. This is the lambda h. Alright. Now, similarly, if I write for lambda d, I can write it. Lambda d will be the same thing, just the difference will be mu d. The lambda d will be 3 by 4 mu d E4 8 epsilon naught per square h cube c. Alright. So difference in wavelength delta lambda can be written as lambda d minus lambda h. If I write it, the only point of difference will be mu d minus mu h. Then mu d minus mu h, and I also have a lambda h in delta lambda upon lambda h. So I'd have a mu h in the denominator also into 100. No, but we have to calculate further. So this is a more calculative question. Okay. So moving forward, I can open it up. I have to split it open. Alright. Now, whatever we have written mu d minus mu h upon mu h, we have to write the whole thing. So mass of electron m deuterium all divided by mass of electron plus m deuterium minus mass of electron m hydrogen divided by mass of electron plus m hydrogen all divided by mass of electron into m hydrogen divided by mass of electron plus m hydrogen into 100. All it. Now, so mass of electron plus mass of hydrogen divided by mass of electron plus mass of deuterium upon mass hydrogen minus 1 into 100. So delta lambda upon lambda h into 100 can be written as what? Okay, I can write it as mh upon md into md upon mh 1 plus me upon mh 1 plus me upon md. Alright, minus 1, and whole thing multiplied with 100. Now, if I use the binomial, because this will just cancel out, and since the value of it is very small, 1 plus a, and a is less than 1, so I can just write the whole thing as 1 plus me upon mh times 1 minus me upon md minus 1, whole thing multiplied with the 100, because we have to get the percentage change. Alright. So now we are done. You just have to put the values for me, mh, me, md over here and multiply it by 100. So whatever the answer will come, that will be the answer for the question number 25 for you. So now moving on to question number 26. Question number 26 over here. If a proton had a radius r and the charge was uniformly distributed, calculate using Bohr theory the ground state energy of H atom, then case 1 is r equal to radius equal to 0.1 angstrom, and case 2 is when radius is equal to 10 angstrom. Alright, so these are the two cases over here. Okay, so in an H atom in ground state, electron revolves around the point-sized proton in a circular orbit in Bohr's radius. So we already know that the MVR should be an integral multiple of H and mv square by r, I can write it as minus 1 upon 4 pi epsilon naught e square upon radius v ka whole square. Alright, so m upon rb minus h square upon m square rb ka square is equals to e square upon 4 pi epsilon naught rb ka square. So the kinetic energy K can be written as half mv square, which will be m by 2 v h upon mrb whole square. So you get this, and v are equal to h. So v can be written as h upon mv. Okay, m upon r. All right, h upon mrb. So you already know this, that h square upon 2mrb per square is equals to 13.6 electron volt. So the potential energy of the electron in this atom will be potential energy Pe will be 1 upon 4 pi epsilon naught minus e square all divided by rb. It is minus 27.2 electron volts. Total energy will be kinetic plus potential, so plus 13.6 minus 27.2. It will be minus 13.6 electron volts. So when the radius, now starting from here, when the radius r is equal to 0.1 angstrom, so r is less than rb, where rb is what? rb is 0.51 angstrom, and the ground state energy in the same operating condition for the proton is minus 13.6 electron volt. So, and this is r is less than rb for this case, and in the second case, when r is equals to what? 10 angstrom, then r is greater than rb, because rb is 20 times smaller than this value. 20, no more. 40 times smaller. Right? So now solving for this. Okay, this is also a calculated question. So now if I write r dash b will be equal to what? 4 pi epsilon naught h square upon m e dash, where replacing e square by e dash, where e dash is the charge on the sphere of the radius. Alright, so e dash can be written as e upon 4 pi by 3. Alright, 4 pi by 3 r cube into 4 pi by 3 rb dash ka whole cube. Alright, so I can write it as r dash b ka cube divided by r ka cube. Simple. Now rb dash raised to the power of 4. If I r dash b ka cube, if I take the other side, it will be raised to the power of 4. It will be 4 pi epsilon naught h square upon m e square into r cube. Alright, so now this part is already 0.51 angstrom, and r cube 10 angstrom ka cube 1000, so it will be 510 angstroms. Now for the second part, so r dash b is equal to 4.8 angstrom, so which is less than r equal to 10 angstrom. So kinetic energy, first of all, k dash will be equal to half m v dash square. It will be m by 2 h square upon m square rb dash square equal to h upon 2 m rb dash square. So h square upon 2 m rb square rb upon rb dash equal to 13.6 electron volt. Okay, 13.6, 0.51 divided by 4.8 electron volt cancelled out the whole square. So calculating for this. So this value will be what? 0.16 electron volt. 16 electron volts. Okay. Now, potential at a point inside the charge proton will be equal to k constant E by r 3 minus rb dash ka square upon r ka square. Okay, So KEE 3R square minus RB dash का square whole divided by R cube. So potential energy you will be minus EV. Okay, EV is the potential. So just writing for the potential minus EKEE 3R square minus RB dash का square whole divided by capital R का cube. Alright. Now E square upon 4 pi epsilon naught RB minus mu RB 3R square minus RB dash squared whole divided by R cube. तो इतने की वैल्यू तुम लोग को पता है -27.2 इलेक्ट्रॉन वोल्ट्स और अंदर वैल्यू होंगी एंगस्ट्रॉम में तो 0.51 एंगस्ट्रॉम 300 minus 23 angstrom whole divided by R cube यानी 1000 angstrom. Okay, so angstrom सब cancelled out. And इसकी टोटल एनर्जी अगर निकालेंगे तो आएगी -3.83 electron volts. So total energy will be kinetic plus potential. It will be 0.16 electron volt minus 3.83 electron volts. And this I can write as minus 8.67 electron volt. Lengthy question. Okay, so question number 27 now. So in the Auger process, an atom mazes a transition to a lower state without emitting a photon. Alright. The excess energy is transferred to an outer electron which may be ejected by the atom. This is called an Auger electron. Alright. So assuming the nucleus to be massive, calculate the kinetic energy of an n equal to 4 Auger electron emitted by chromium by absorbing the energy from n minus 2 to n equal to 2 to n equal to 1 transition. Alright. So first of all, we have to know what is the Auger effect. Alright. So Auger effect is a process by which basically the electrons with their characteristic energies are ejected from the atoms when a downward transition by another electron in the atom has occurred. Alright. So like initially what the spectral lines were observed now. So now what happens is the energy that is released when an electron moves down from a higher energy state to a lower energy state. This energy will basically make an electron jump out of their place. So now the spectroscopy of Auger is when the vacancy is produced by that bombardment with high energy electron. But this Auger effect can occur if the vacancy is produced by other interactions. Alright. So if an inner shell electron is removed from an atom, alright, then an electron from a higher level will quickly make the transition downward to fill the vacancy. Got it? See, in the inner shell electron is moved from an atom. Alright. So like what happens is I'm drawing this is the low energy states and these are the high energy states. Alright. Think of it like this. When this electron will jump out of here, there will be a vacancy produced over there. Vacancy. So an electron revolving over here or over here will jump to fill this place. Now this electron is coming from a higher energy state to a lower energy state. So sometimes this transition will be accompanied by what happens is a photon can be emitted whose quantum energy will match the energy gap between the upper and lower level. See, whatever energy high, energy low. So what will happen? The released energy will be definitely EH minus EL. Alright. It will always be this. So it can be in the photon case or in the it can emit also the spectral lines. So if there is a photon emitted, then its quantum energy will match this energy gap EH minus EL. So In another case, we can talk about when the energy is released by downward transition, it is given to the outer electron instead of a photon. The electron which has moved out, this energy can also be given EH minus EL can also go to it, can also go to a photon. Alright, these both cases are possible. We have to know this. Alright. So if this electron is ejected from the atom with an energy equal to this, it will move with some kinetic energy. So the energy lost by the electron, which is made by the downward transition, minus the binding energy of the electron that has been ejected from the atom. Alright. So this is basically, this is the whole concept behind this. Okay. If I'll draw this diagram for you to understand this. So this is the outer shells of an electron. Alright. Now what happens is this is the inner shell, and a high speed electron is coming from over here. Electron with a high speed has come, and it bombarded with an electron which was over here. So this electron was overthrown. This is moving out. Alright, and electrons are here, electrons are here as well. So sometimes an upper electron will drop to fill this vacancy. What will happen? There's a vacancy over here, na? So this vacancy is getting filled by one of these electrons coming down, or one of these, which are at a further higher level of energy. Okay. So since this energy is coming, since a heavy atom, X-ray or fluorescence can be seen, but what will happen is there will be some energy which will be like I've shown you, EH minus E low. So the electron which has been shot out of here, this is called the Auger electron. Alright. So moving back to the question now. Okay. So Auger process की पूरी बात हुई थी, and we can write the energy as plus Z square R 1 upon N high square minus 1 upon N low square. Alright. So Z square R 1 minus 1 by 4 will be 3 by 4. Okay. Since N2 equal to 2 na, so Rydberg constant, if I write the energy is equal to 3 by 4 Z square R. So the energy required to get an electron from N equal to 4 state to that state will be what? Z square R 1 upon 4 plus square 16. So it will be 1 by 16 Z square R. Right. The energy required to eject an electron from N equal to 4 state we have calculated. Now this will be equal to the difference in energy will be equal to the kinetic energy. So En minus E4, we can write the kinetic energy as Z square R 3 by 4 minus Z square R by 16. So now I'll write it as 11 upon 16 into 24 into 24 into 13.6 electron volt. So it is basically what? So it is 5385.6 electron volts. So the inverse square law in electrostatic has been given to us. We already know about this. For the force between an electron and a proton, the 1 upon r dependence of F can be understood in the quantum theory as being due to the fact that the particle of light is massless. If photons had a mass mp, force would be modified to this. Alright, so estimate the change in the ground state energy of H atom if mp were 10 is to the power minus 6 times the mass of an electron. So it is basically just to solve. It is also a lengthy question, but I'll try to do it quickly now. Okay, so mass of proton, mass of electron, we already know. Alright, now and we are equal to nh upon 2 pi, right? So h upon 2 pi, and v equal to h upon mr. So writing down over here, and v square upon 4 pi epsilon naught 1 upon r square plus lambda by r. Alright. Therefore, force we already know can be written as E square upon 4 pi epsilon naught r square 1 upon r square plus lambda upon r. E is to the power of this. So equating the forces, I'm going to get h square upon mv equal to E square upon 4 pi epsilon naught 1 plus lambda r. Okay, so h square 4 pi epsilon naught and E square will be, I'll put r over it, r plus lambda r square. So if I neglect r square and lambda equal to 0 for r equal to a, what will I get as it? H upon m equal to E square upon 4 pi epsilon naught r ra. Right. Now quickly moving forward, if I consider the potential now, if I consider the potential VR will equal to minus E square upon 4 pi epsilon naught, putting the limiting values over here, minus E square upon 4 pi epsilon naught r a and E minus lambda r 1 plus delta upon r a raised to the power of, delta upon r a raised to the power of minus 1. Okay, and now I'm going to get what? Minus E square E minus lambda r 4 pi r epsilon r a 1 minus delta upon r a. So the potential VR equal to minus 27.2 electron volt. It will remain unchanged. Alright. Now the kinetic energy K can be written as mv square by 2 and half m h upon m r ka whole square. So it can be written as h square upon 2 m r square. And solving for this, I'm going to get 13.61 plus 2 lambda ra. Alright. So the total energy can be written as minus 27.2 plus 13.61 plus 2 lambda ra electron volts. Alright. So if you solve for this, you will get the answer for this question. Now, the last question for today is question number 21. So the Bohr model for an atom relies on Coulomb's law of electrostatics. Coulomb's law has not directly been verified for very short distances of the order of angstrom. Supposing Coulomb's law between two positive charges is modified to this. Alright, calculate in such a case the ground state energy of H atoms if epsilon is 0.1 and radius is 1 angstrom. So I can write it as like this: force is equal to Q1 Q2 4 pi epsilon dot r naught raised to the power of delta. E, and E has been given as 0.1. Okay, right now that it as delta and R2 plus delta. So V square can be written as R naught delta upon n r1 plus delta. Okay. So m v square upon r is equals to x r naught delta upon r2 plus delta. So v square can be written as x r naught delta upon m r1 plus delta. So mv are equal to nh. Okay. R can be written as nh upon mv, can be written as nh upon m, n upon x r naught delta raised to the power of 1 by 2 and multiplied with r 1 plus delta into 2. Now solving for r. If I solve for r, radius Rn can be written as n square h square m x r naught delta 1 upon 1 minus delta. And if I take n equal to 1, subtracting the constants, r1 will be equal to h square upon m x r naught delta 1 upon 1 minus delta. R1 can be written as 1.05 plus square into 10 is to the power of minus 68 whole divided by what? 9.1 into 10 is to the power of minus 51 into 2.3 into 10 is to the power of minus 28 into 10 is to the power of 19. All it, and this whole 1 divided by 2.9 because delta is equal to 0.1. So if you will solve for this, you'll get the radius r is equals to 8 into 10 to the power of minus 11 meters. So it can be written as 0.08 nanometers, so which is less than 0.1 nanometer. So this is the radius of orbit of electron in the ground state of hydrogen atom. So again, using the Bohr's second postulate for the speed of electron, this is it. We got the radius right now. So now moving forward, the velocity v will be equal to nh upon mr, writing it nh mx r naught delta m square h square, and same thing 1 upon 2.9. So the kinetic energy, now I'm writing it half v1 square minus 9.43 to 10 to the power of minus 19 joule. The second get as 5.9 electron volts. Now the potential energy U will be 0 say R naught F times dr. 0 say R naught x upon r square dr minus x upon r naught. Potential energy from r naught to r. Okay, from r naught to r can be written as x r naught delta upon r2 plus delta dr. Okay, so if you integrate this, what am I going to get? Upon 1 plus delta 1 upon r 1 plus delta minus 1 upon capital R 1 plus delta. Okay, so x upon 1 plus delta r naught delta r 1 plus delta minus 1 upon r naught. So putting the values over here and solving 2.3.0.9 10 is to the power of minus 15. Under diagram 0.8 to the power of 0.9 minus 1.9. तो इसको सॉल्व करेंगे, आंसर will be minus 17.3 electron volt. Now the total energy in the electron ground state will be minus 17.3 electron volt plus 5.9, because this was only the potential energy previously calculated. For the kinetic energy, it will be minus 11.4 electron volt, which is in contrast to the minus 13.6 electron volt energy that we previously used. So hence we are done with this topic of atoms, and I'll see you in the next session with a different topic. All the best. Thank you.